Yeah.
Yes.
Yeah, cool. Thank you. So yes, I'm from NIASRA at the University of Wollongong. I'm actually one of the statistical consultants at NIASRA, part of the Statistical Consulting Centre. But we also have, environmental stats at NIASRA. We've got survey stats, a Centre of Survey Stats, a Centre of Social and Health Stats Analytics, and we're also doing a new data science initiative as well. So we are doing exciting things at NIASRA, and I'm very happy to be a part of it. I only just finished my PhD, submitted my PhD, and then joined the team. And I also did my PhD at Wollongong Uni. So, and that was with Yanjia Lin and Paulina Shaughnessy, and also Andrew. So I will just give a little bit of a brief introduction of what I'm interested in. So we were looking at the synthetic data problem from a statistical disclosure control perspective, and that is pretty much how do we share data in a way that is responsible to not violate the confidentiality requirements of any of the participants whose data we have collected. And there's two kind of main strands of approaches people use. There's access control, which I think anyone who's ever tried to get data before would have been familiar with, and that's usually some kind of rules-based approach to getting data. So you have to either come on to whatever organization's premises, or you can only get certain aggregations of it. The other strategy people use is in statistical disclosure limitation methods, and so this usually requires some kind of perturbation or some kind of introduction of uncertainty into the underlying data, which should obscure the identities or protect the responses of any of the participants. So we have two main formats in which we consider protected data, aggregated data and microdata. So if you hear those terms, that's what I'm referring to. And aggregated data is just data that's been tabulated or summed in some way. And microdata are the individual records. That's the transactional level data that we are often interested in and are often the most concerned about, because that's where a lot of the privacy risk comes into it. And so one of the biggest misconceptions we have with statistical disclosure control is that people think that just because they've removed their names or the addresses from data sets, that means they're private. But de-identified does not necessarily mean private. And especially nowadays when we can link and match observations, there's much more external information available to the public. And so especially if we think about continuous data, the chances of matches across data sets would be much smaller. And so the ability for us to maybe use some kind of external data to match it to our de-identified microdata, we can then use that to gain inference on the identities of the participants. So we have to be a little bit more careful, and it's really hard to actually measure the disclosure risks in microdata sets, but it's just something we have to take a lot of notice of, especially if we are dealing with really sensitive information. And so usually the question we face in statistical disclosure control is whether or not we should perturb the data. When I say perturb the data, I mean add noise to it, obscure it using some kind of transformation, but usually some random noise. And the biggest problem with perturbing the data is often, I've got this little graphic up right now, but you have to put in quite a lot of error in order to really protect people's identities. And by the time you put in quite a lot of error, you end up just ruining a lot of the statistical utility to it. And what we don't want to do is be so concerned with confidentiality that we end up releasing useless data. So we have to try and find that balance. And so ideally we want to produce a sample that looks like the original data. And, we all kind of are familiar with simulating random samples from distributions. And so ideally we would like to see kind of a resampling or a sample of a hypothetical population and release that data as opposed to the individual responses. of people, and this is what synthetic data is kind of all about. But ideally, we need to know what the density is. And, you know, we had some great talks before where we talked about different ways of really trying to estimate the underlying density, you know, whether it's through some kind of model or some of the machine learning techniques. So there's a couple of existing methods. One of them is the kernel density estimate. This also exists in the joint density form, but one of the issues with the kernel density estimate is that it is like a kind of smoothed version of the histogram. And because of that, we can end up simulating data out into the extremes where we might have only seen 1 or 2 observations. And often, because it's a local estimation method, you get a lot of clustering on these outlier points. And so ideally, we want to try and use something that's a bit of a global estimate that mitigates the risk of relying too much or being too influenced by outliers or extreme points. We could use a copula. You know, copulas have been shown to be very useful, and you know, this is an example where it gets a pretty good estimate of the density function. But sometimes copulas don't work. Sometimes, you know, it might not be as robust to the underlying density. And, you know, if we're trying to look at this as being a robust method that can be applied to lots of different data sets, we have to try and think a little bit outside the box. So what we said is we need a method that uses global parameters to fit the density, so we don't get any kind of local concerns. But we also need it to be pretty robust, so it can pick up pretty strange atypical densities as well. And we don't want to assume too much. We don't want to have too strict conditions on the distributionary assumption. And so we looked at some of the mathematical and approximation theory results in this space and proposed this multivariate moment-based density estimate. Now, there's a lot of maths there, but don't worry. All we do is pretty much apply an orthogonal polynomial expansion of the density function over, now it says they're a compact space, which means a bounded space, but we can generalize this to unbounded spaces for certain circumstances. It's just not necessarily guaranteed. Whereas on the compact space, we know from the Weierstrass-Stone approximation theorem that this thing will converge. And so we usually can restrict ourselves to that. And we find that in practice, you know, assuming a bound to your overall sample space isn't too problematic. You know, just usually we have bounds in our samples. And what we end up with is our coefficients just being functions of the sample moments. But I will just say, you know, there is a problem with this form in using it in practice, in that we've got some infinite summations there. And so we can't actually infinitely sum this thing. We're going to have to do some kind of, you know, truncating of the upper end terms. But we do know that it will converge. So provided we take sufficiently large K, we can get something that's reasonably good, but we will introduce a little bit of bias. And we don't know the true moments in practice, but we can use the sample moments to get an estimate of those. So that's going to introduce sampling variance into our estimate as well. So we've got this kind of trade-off in our density expression between bias and variance, a classic kind of trade-off we see in lots of estimators that we have to deal with. And I'm not going to really go into how we optimize this, because we have done quite a bit of work on how we actually determine the K and how do we best select the density estimate we're going to be using. Instead, let's just have a look at an example. So I've got a normal gamma distribution here. I actually do know the true density for this one, but in practice we mightn't. And we can have a look at how the density estimate converges towards the true underlying distribution of the data as we increase that max polynomial order. And so you can see it gets pretty good, but then it starts to diverge again. This is partly due to the numerical properties of just actually calculating it. You have little errors in that, and by that stage you're going to be introducing a lot of that error. But it's also because we're going to be using so many higher order moments that it will increase the variance in this estimate, and it's not going to be very good. So we have to try and, in practice, we always select a K that's actually, not too large and doesn't cause too many computational problems. All right. But what does all this have to do with synthetic data? So a moment-based density approximation, it uses aggregated data in order to estimate the density. So importantly here, we only used the sample moments to get a density estimate. We didn't have to use any of local information. The other thing is, because information cannot be created, that means that we've kind of removed a lot of that, what we would consider the most risky aspects to releasing microdata. We've just got the moments. You can still, do inference on that, but it just lessens the risk of violating people's privacy. We don't see those sharp peaks in the tail of the distribution, so we're much more resilient to the effect of those outliers. And I think what I'm most interested in is that because these are just solutions to Sturm-Liouville DEs, these are just orthogonal polynomials, I've got an analytical expression of my density estimate. I also can then get an analytical expression of my cumulative distribution function, my conditional distribution functions. And because of that, I can then fairly simply, using Gibbs sampling and other MCMC methods, generate a synthetic data sample using inverse transform sampling. So it's quite a nice expression we end up with. And because of that, we can do a lot of inference that perhaps you mightn't be able to if you use something that was strictly a machine learning based technique. All right, so let's have a look at a particular case study. This one here is a sample from the ISLR package in R. We just took, we actually only have one continuous random variable here, and that's the wage, and the other three are categorical. And what we do is we fit the density estimate on a continualized version of those categorical data. So I haven't really explained it here, but we convert categorical data into continuous data by use of some just kind of noise distribution with set bounds that I can then recategorize afterwards. And by doing that, I can fit, for any kind of combination of categorical and continuous, it doesn't just have to be strictly continuous data sets. And so when we do that, we get out this histogram of the wage data. So you can see kind of down, can I point? Yeah. Down here, we see a bit more of a flattening over those sharp peaks. And that kind of just obfuscates the risk of those particular observations. That also kind of happens out here with these points as well. And so that's because we're using a global approach, we're using sample moments. So in the tails of the distribution, we see less influence in the sharp peaks from outliers. This is when we compared our categorizations, our counts. We can see pretty good consistency between where each thing falls. There is slight variations, especially in the areas where we don't have a lot of data. I think there was only like 8 observations that fell into this category. So you see a bit more random variation there. But from a privacy perspective, we kind of think that's a good thing because they're the people who are most at risk. So you would like a little bit more variance in those kind of low data spaces of the sample space. I can overlay some box plots and we can see that, we don't have, this is an outlier here in a pretty extreme sense. We don't have any exactly corresponding, but we still get to see points that fall out in that space as well. So we still get similar, but not exactly the same. And that's kind of what you want in the synthetic data. You want something that's got similar kind of properties, but not exactly the same. Here we do see a matching up, but remember this is marginal. So at that point on the job and health categorizations don't match. So there's nothing that actually perfectly corresponds to each other, which is important to say. But we're getting pretty good consistency on all of it. The other thing is because this is a density estimation method, it's not just fixed to be fit for the same moments and things. We also see consistency in our linear regression coefficients. There's slight variations, but not just that, even in the standard errors of our linear regression coefficients I could show you tables and tables where we get consistency with our squared values and all sorts of things as well. When we go to the general linear regression, we see a little bit more variance in that, but it's still fairly good. We all make the same conclusions after the hypothesis testing and get pretty consistent results with our coefficients as well. And the last thing I will say before I finish is, when we consider these kinds of methods, we always talk about disclosure risk associated with it. Now, this is just a pretty simplified explanation that because we have condensed this down to just the moments, there is infinitely many, as long as we make sure that we have less coefficients than observations, there's always going to be infinitely many combinations of data sets that could have produced that set of coefficients, which creates a privacy thing. But we should also be wary of other kinds of disclosure risks. So this whole topic, there's another 2 chapters in my thesis to talk about on that. So I won't go into it now. And I think that's about it. I will just say, though, that there is no perfect solution to this microdata problem. Some methods are going to work better than others in certain situations. But this is just another solution that we've been working on to try and answer this problem. How do we release private data in a way that protects people's privacy? So yeah.